Welcome to Mathematical Methods Session 1. I'll talk to these things at the start of next year. Session 1 concentrates on calculus and in particular the rule y equals a x to the power of n. Remembering that you bring the n down and multiply, then you minus 1 on the n. What might that look like? Y equals 4x to the power of 3 becomes dy dx equals 4. The 3 comes down and multiplies. X to the 3 minus 1. That's going to be 12x squared as being my final answer. If we have expressions that are in factorised form, then we need to expand the brackets to get it into this form to then apply that rule. If we have fractions, we represent them separately as 4x squared over x minus 3x over x. And what that looks like is this. So this expanded gives me this expression. The derivative of 2x cubed is 6x squared, negative 4x squared is negative 8x, 6x is 6, and the derivative of negative 12 is 0. The same with this example, and these give me two separate fractions, both over x. When you cancel, you lose the x in the denominator, so you need to include the restricted domain since the implied domain has been lost. Now you can take the derivative of 4x minus 3 gives you a 4. When it's in rational powers, you can do the same thing. For example, y equals 1 on 4, x to the 1, negative 1 quarter. I bring the x component up to the numerator, and then you can take the derivative. Dy dx would equal 1 quarter times negative 1 quarter times x to the negative 1 quarter minus 1, which is going to be negative 1/16, x to the minus 5 on 4, which could be simplified to equal negative 1 on 16 x to the 5 on 4, making the power of the x positive by taking the x expression from the numerator to the denominator. Here are those other examples for you to look at. The chain rule is used when the expansions that we did up here become too cumbersome and difficult and too many steps. So I could expand y equals this squared quite comfortably, but coming to the power of 5 or coming to the power of 15 is really making it a lot of work. So the chain rule is going to come in handy. The chain rule is dy dx can be expressed as the chain of derivatives dy du times du dx. And you'll notice that the du's will cancel to leave a dy on the numerator and a dx in the denominator. So what does that look like? If I had y equals 2x minus 3 to the power of 5, then the u bit is the bit inside the bracket. So the u bit is 2x minus 3. So du dx is 2, which makes y equal to u to the power of 5, since the bracket 2x minus 3 is what we called u. So dy du is 5u to the 4. Putting that together, dy du is 5u to the 4, du dx is 2, 5 times 2 is 10. Substitute back 2x minus 3 for u, gives me that expression. It's a quicker way than expanding this bracket to the power of 5. What might that look like over here? I'm going to make u equal to x squared plus 5x minus 12. Therefore, du dx will equal 2x plus 5, and y is going to equal u to the power of 6. So dy du will equal 6u to the power of 5. So dy dx is dy du times du dx, and that will be 6u to the 5 times 2x plus 5, which gives me 6x squared plus 5x minus 12 to the power of 5 times 2x plus 5. There's another example there. I would rewrite that as y equals x squared minus 10 to the half then make this bit x squared minus 10 equal to u, which is what happens down there. So that's the chain rule. To assist where we have things that are raised to a large power or underneath square roots and the like. It's an irrational number, roughly 2.7. It's not the same as the variable. And in Year 12 methods, our go-to exponential is base e, and our go-to logarithm is base e. On the calculator, log base e is written as ln on the calculator. So where is that on the calculator? So if I'm looking for e, I'm not going to variables. In main Math 1 keyboard, there's e, and you raise it to the power, so e to the power of 1 is going to equal e, which is 2.718, etc. It's a non-repeating irrational number. And here is ln, the natural logarithm, and it's written as ln on your calculator. I'll talk more next year as to where it comes from, but just for us for today, if the function is equal to the expression e to the x, then the derivative is also equal to e to the x. And if the expression is log base e of x, then its derivative is 1 on x. The derivative of sine is equal to cos of x. The derivative of cos is equal to negative sine of x. And the derivative of tan is equal to 1 on cos squared of x. The reciprocal trigonometric functions have particular names, and they're just like nicknames. 1 on sine is cosec, 1 on cos is sec, 1 on tan is cot, which means if on the previous page we said that the derivative of tan was 1 on cos squared, then 1 on cos squared is the same as sec squared. And you'll find that this is what they write in the VCAA formula sheet for the derivative of tan. So what might some of these examples look like? Well, if I was to do this one here, I've got y equals e to the 3x plus 2. I have a chain rule. I know that when y equals e to the x, the derivative, y dash, is equal to e to the x. So I'm going to make u equal to 3x plus 2, which means that du dx is equal to 3. And y now equals e to the u, which means that dy du is going to equal e to the u. So dy dx should equal dy du, du dx, which is going to be e to the u, because dy du is e to the u, times 3. And substituting that back, I get 3e to the 3x plus 2 is what dy dx looks like. And the 3 other examples there I've written. So some more examples. If I wanted this one, u equals x squared, therefore du dx equals 2x, and that y equals e to the u, dy du is going to equal e to the u as well. So dy dx is going to be dy du times du dx, which is e to the u times 2x. So 2x e to the x squared will be the derivative. 3 other examples there, and I've got worked solutions for you in that particular instance. So today's homework is 9E, F, G, H and I, Tech Tasks 1, 2 and 3, and the My checkpoints, which are explained in the main document.